Yeah, please. First of all, I want to thank everybody for taking some time to do some learning today with our program. I think you're going to find will be very interesting. We have had over 50 programs so far, and we've had various people to thank for helping them happen. And presently, we're indebted to Dr. Clement Schwartzinger and the university where he works for the use of their Zoom program and their storing of our programs there, which is much appreciated and allows the public to see programs that they might have missed. This is our hope that we'll actually have all the programs that's at one point that have been done, collected, and available. We've been doing this now since November 2020. Gemquest is a nonpartisan nonprofit program whose aim is to give educational opportunities to those who are interested in expanding their knowledge of gemology, geology, and mineralogy in association with gems and jewelry. But today we took a 180-degree turn from that tradition, and I thought it would be of great interest to anybody who's involved in the jewelry business to learn a little bit more about the metals that we wrap around the stones that we love, those being gold, silver, and platinum. Now, I'd like to say that I I'm comfortable and knowledgeable in these areas, but I have a feeling my knowledge is a fraction compared to the presenter we're going to have today. Now, I do remember at one point hearing a quote from Einstein that said that the sign of a truly intelligent person is the ability to transfer and translate complex scientific and philosophical concepts into every man's language. And the presenter we have today is someone who is not only of that intelligence level that can do that, but he's also a gifted presenter. And I've heard him speak, and I just said to him, I didn't even let him get past me in the aisle when he was leaving. I said, please, would you present to us on Gemquest? Because I think people would like to hear what you have to say. Now, the presenter we have today is Dr. Terry Wallace. He's the director emeritus at Los Alamos National Laboratory, which, if anybody knows anything about science, is one of the nexus points in the world of science and has been highly respected as a source for education and scientific research for decades. He was the 11th director of the laboratory. Previously, he was the principal associate director for global security and senior intelligence officer. He received his BS, notice that's BS, right? Degrees in mathematics, sorry about that, and geophysics from New Mexico Institute of Technology in 1978. My God. And a PhD in geophysics, and particularly in seismology, from the California Institute of Technology, which seems to be quite appropriate since they have an awful lot of seismic activity there, in 2003. Dr. Wallace served as a professor of geosciences and an associate in the applied math program at the University of Arizona for 20 years. Dr. Wallace is a fellow of the American Geophysical Union, AGU, and in 1992 received the AGU's McIlwain Medal. He served as president of the Seismological Society of America, chairman of the Incorporated Institutions for Research in Seismology. So when there's shaking going on, he knows all about it. He's also an expert in mineralogy, which is sort of helpful in this world that we live in, and received the Carnegie Mineralogical Medal in 2003. And I'm sort of proud to know that two Canadians in a row have also shared that honor in the last 2 years. And this was in recognition of his contributions to mineralogy and mineral preservation, and to give testimony to his ability to communicate about things to do with his interests. He has published more than 30 articles and books on minerals for public consumption. So I don't think I'm going to take any more of your time in introducing him. I'd like him to share with us today a bit of his knowledge to do with the jewelry metals that we wrap our stones in, gold, platinum, and silver, and their history. Please, would you welcome Dr. Terry Wallace?
Well, good afternoon. At least it's afternoon here in Colorado where I am, where we had a snowstorm last night of about 4.5 inches, which is always a kind of a Colorado spring. But I'd like to be able to talk about, in particular, gold, silver, and platinum. They're shiny metals that attract the eye. They certainly captivate the soul. But these metals have played a pivotal role in fine jewelry, from simple rings to accents that highlight precious gems in brooches or necklaces. The story of jewelry, though, our jewelry metals, is part science and part aesthetics. However, I think the narrative is likely much deeper than most people realize around science. It is a truly cosmic tale. Now, these metals were forged in the most violent furnaces of the universe, and then they were scattered across the nearly unimaginable vastness of an empty space called our universe, and ultimately were collected together in some kind of tremendous gravitational storm that built our solar system some 4.5 billion years ago. A modest amount of these metals were collected out of this nearly empty space, really atoms only, and collected into rocky masses of rubble that became Earth. Our planet then functioned as a furnace and factory in their right or on their own to transform these metals into fabulous minerals. And mankind eventually came by, mined these minerals, refined the metals, and then crafted them into works of art or jewelry. Carl Sagan stated that the cosmos is within us. We're made of star stuff. We are a way for the universe to know itself. The jewelry metals tell a very special part of that universal history, which to me makes the individual piece of jewelry much more than a pretty pendant or a nice necklace. These metals are what I would call strands of DNA of what the universe is. And so when I talk about these, I'm going to try to give you a picture and walk down as the way I see them. And so I'm going to give some simplified science. I'll make some people cringe when we talk about the science of this, but I want to give a picture of how they work together and then bring it back to the relationship to mankind. So the first place to always start when you do this is to talk about the periodic table. Everybody recognizes the periodic table no matter what your background, but not everybody has a full background in that. In fact, almost everybody thinks of it as the spreadsheet that they learned in high school chemistry. Our average collective memory of this is periodic table is pretty abbreviated. You probably remember that there's like about 92 natural elements found on Earth, and maybe something like the symbols for those, Ag for silver or maybe Au for gold. But the periodic table is what I would say is the single most important achievement in human history. It arranges the 118 known elements, 92 natural ones, like I said, and maybe 26 that have been created in a laboratory or a reactor, into a simple pattern that reveals its properties. And these properties are very much a signature of how things are formed and how things will form. And so together they are an incredible, like I said, spreadsheet that you can learn from. I've circled the jewelry metals, and they're the intersection of two prominent groups that most people know. There's the coinage metals, copper, silver, and gold, which are some of the oldest metals utilized by mankind. And then the platinum group metals, and you see PT is the same for platinum there in that circle. And so they are all kind of similar where they are on the periodic table. And so they have some similar traits, some differences too, but it's these traits that make these metals really interesting to us. If we look at this, we'll start to look at that coinage metal column. These are something that everybody knows because we call them coinage metals because they're non-corrosive and they've been used as a way to move from a pure barter system to an actual accounting system for the last couple thousand years by making something that you carry around with some value. And if we look at that, they're in what we call this group of the periodic table, which is group 11, and they're defined by their electron configuration. They have one s orbital electron above filled shells. That doesn't mean a lot to a lot of people, but it does mean that they have a valence electron, something that allows them to combine with something else, but it's tightly controlled. And so they behave similarly, but not exactly the same. But silver and gold are pretty spectacular because of that electronic configuration. And I want to go and look at a little bit of those things and then come back to platinum. So gold and silver, but gold in particular is incredibly ductile. I mean, you could take that material and it can be drawn into the thinnest wire, and a single ounce of gold can make 50 miles of thin wire that's only 5 microns thick. think about the ductility itself is something that you would be, certainly makes it of something fine for jewelry, but it's one of those characteristics that have to do with how that metal or metals in general, but that metal in particular are configured and how it shares its electrons. So again, you see the periodic table with these Cornish metals standing out here. The properties that they share is they're all ductile. They all are good conductors of electricity because they have a metal cation that gives up an electron quite easily. Silver is, in fact, the singles for a metal or any single element is the strongest conductor of electricity known. They're very shiny, at least in most of the visible spectrum in terms of this. And they're fairly, as I said, non-corrosive. When we say non-corrosive, that means they're not easily uh, converted away from being just a native element. When I look at these kinds of metals and think about what you have in terms of these things, it's important to think about their characteristics as compared to other kinds of materials in the periodic table. They can combine through this valence electron or valence electrons that are available in all these, but they can also be found in nature as a native element. There are only about 17 elements that can be found native in, at least on our Earth, in terms of native things or metals. And these are the three most significant, at least as far as mankind is concerned. The platinum group are a really fascinating group of elements. And so you pull them out. We usually group these as six different elements, but the ones that most people are most familiar are platinum and palladium. If we look at these, the things that are amazing about they're heavy, but they have extremely high melting points. So if you look at like platinum, its melting point is a little less than 1800 degrees C. So it's a material when found in nature, at least until the later part of the 19th century, couldn't really be processed simply because people couldn't get temperatures that high in a normal furnace. But if you look at something like osmium, which is also in this group, it has a melting point of more than 3000 degrees C. To me, that makes it one of the most fascinating materials that it can hold its configuration even when excited by these tremendous energies associated with temperatures that would reach these high uh, points. What most people think about for platinum and palladium is actually that they're very good catalysts. What does that mean? Well, it turns out their electronic structure is a little different, of course, than we talked about the Cornish metals, and platinum in particular has a electron structure which I would just call sticky. It allows materials like a nitrous oxide or a CO2 atom or molecule to stick to a piece of or an atom of, let's say, platinum. When I say stick to it, doesn't form a bond, but it's like being attached to something loosely like a piece of Scotch tape. That piece of Scotch tape holds that atom or that molecule like a nitrous oxide and allows it to interact with other materials. And in this case, when they interact with other materials, it breaks it into a nitrogen oxygen combination of molecules or some other process, and then it pulls away from this Scotch tape stickiness. So platinum is a very good a very good catalyst to put in cars to basically break down some of the products that we have from burning gasoline and remove them and convert them to more benign products, in particular water or maybe carbon monoxide. So we have these materials that come with them where they are from within the periodic table that bring with them certain characteristics. Now I'm going to keep going down this route just a little bit further. So let's look about when we talk about those, what do they look like when we talk about the Earth itself? What does its crust look like? This is an actual chart that is sort of like a geologist periodic table because it tells you the abundance of any particular elements within the Earth's crust. So we're going to find out that in general, from what we'll talk about today, from how metals or all elements are made through nucleosynthesis and other processes like that, the lighter the element, so hydrogen being the lightest, to the heaviest element, so we go down to uranium. you would expect less and less of the heavier elements to be produced. But if we look at what we see in the Earth's crust, instead of a normal kind of decay that comes down from light to heavy, we see these things which bounce around. So there's a couple things that are going on. One of them is telling us that our crust is doing something, and that's going to be part of a magical engine called plate tectonics. And it's also telling us something about other things in terms of our long-term history and how we produce or how we produce the Earth itself. If you come down here, the rarest metals, that's that little kind of tan region that's in the lower right-hand curve there. You can see platinum and gold are produced almost in equivalent amounts within our crust. We're going to mine much more gold than we do platinum, and we'll talk about why that is in a little while. And you can see silver is just outside what we call the rarest metals. But if we look at that, then the axis that you see over there on the left-hand side is logarithmic. So about 10 times as much silver is made as, or is found in the crust as gold. But that's still going to be something like 10 to the eighth, so 10 or 100 million times more silicon is in the crust than there is any gold or silver. So I'm going to come back to that, but just as a memory, we could see these kinds of things, and we have really rare metals, and then we have other stuff around that may go into gemstones or other materials, but we're going to focus on those rare metals. So to tell the story, it's often easiest to talk about gold to begin with. And one of the reasons it's easiest to talk about gold to begin with is because it's the first real metal that we show up that humanity made a use for, and a use for that showed true imagination. There was a little bit of gold used to make ornamentation, at least from the archaeological record, that maybe something like 7,000 years ago, but very little. And this was, we weren't sure exactly when gold became really important as ornamentation until uh, uh, basically a cemetery or cemetery-like a thing called the necropolis at Varnana was discovered in the early 1970s. And in this case, it's in Western Bulgaria. It was discovered accidentally during an excavation, and a number of graves came up, or graves or grave-like structures. The name is kind of unfamiliar to most of us, but its historical name is Odysseus. So, as the ancient Greeks would have called it, it does bring us, a picture of perhaps Jason and the Argonauts. Well, the graves often didn't contain just skeletons; they contained a tremendous amount of artifacts. And these artifacts, as you can see from, well, this is a grave which is called Grave 43, contained more gold than had found in the entire rest of the world before this grave was discovered from geologic history. So mankind certainly had agriculture, 10,000 BC maybe, and all these other things, but there's very little in terms of jewelry or artifacts until suddenly on stage comes this discovery of a huge amount of gold. In fact, within this um, cemetery area, there's 3,000 gold artifacts, and in this grave, particular the one I show the picture of the fellow in the middle there, more gold was found than that, than contained. Uh, it was almost 6 kilograms, was almost 60 times more than gold had been associated with any human graves before that point. Now, in ancient times, silver was much rarer than gold, and this probably reflects the earliest silver mining, or silver mining amounted to really gathering it in a native state. And silver is much rarer in a native state than perhaps gold, at least on the basis of its abundance. There are deposits in Asia Minor where that was found, but in general, it wasn't until around 2500 BC that there was a major breakthrough in technology. A smelting process was discovered, which basically some silver-rich minerals could be processed in temperatures and through a chemistry process of using ash and bone, be able to pull out some silver. And finally, we're going to eventually get to platinum in a moment. It really wasn't even discovered until the mid of the 18th century. partially because of its rarity and partially because of the difficulty of being able to do much with that. So almost immediately, these metals and their ability to withstand corrosion became the first kind of commerce material that went from accounting that was purely barter to something that had some value. And so the very the very first coin started in Asia Minor, and there's the gold lion is an example of this, and this is one that's from around 600 BC. And these were ways to carry value on based on weight. There's some problems with coins that are like this, of course, is that it turns out that by studying them, you can see these small little scratches on some of the coins, and it turns out that inevitably people began to learn to whittle a little bit off every single coin and collect the gold with time. And so you can actually find as you go in time from 600 BC to around 300 BC, when they stopped using the coins, they tend to get smaller and smaller in weight. The first silver coin is around 500 BC, and this is tetradrachm. This is silver was quite abundant in the regions around Athens, and this is one of these coins you can still buy tetradrachm that from this era for a modest amount of money. When I say modest amount of money, depending on the quality of it, a few $100s. And again, this was I can't overstate how important it was to changing the way um, commerce or how civilizations could keep moving forward in terms of accounting or putting value to things. When we look at the total amount of silver, gold, and platinum that are in mined, you would expect it to be kind of like its abundance. And indeed, if you look here, the total amount of platinum that's been mined, and I could put it in, it's like 90, 9,400, 9,500 metric tons. It's kind of easier to think of it as cubes and look at the volume so we can do a comparison since they have different densities. It's like a 7 meter cube on its side, 7 meters on a side cube. The amount of gold is 20 meters on the side. And then for silver, you can see something that's much larger, a factor of three larger than that. Of the amount of material that's been mined here that's been re-recovered through recycling. So it's still around today, or on an annual basis. Instead of mining silver, for example, it's taken out of electronics, is about 90%. So very little of this material disappears. So unlike some other geologic materials which we may observe, use once, go away, these stay within the system. And that again attributes to both their value and the fact that they're materials which are necessarily non-corrosive. But the real science story about why these metals are the way they is you have to go back to the very beginning of the universe. And so the cosmic journey of jewelry metals, that strange metal that we so adore at least in our jewelry, is really not of Earth. It's not of a mine today. We really have to go back to 13 and a half, maybe 14 billion years ago and look at the Big Bang. So when we look at the Big Bang, that's a picture that's depicted here graphically with not only the particles that most of us are used to in nuclear physics of protons, neutrons, and electrons, but leptons, hadrons, quarks, and everything else. They suddenly appear. And as the Big Bang began, in its smallest fraction of time that we can imagine, 10 to the minus 32 or 31 seconds, a Big Bang occurred and spewed forth material that slowly coalesced, and I say slowly, within something like a microsecond, and began to form the particles we're more familiar with, protons. Or maybe after a few minutes, we began to form a few elements like hydrogen or helium, or maybe a fraction, a tiny one, slightly lithium. And as this material began to happen and move out, you begin to get heavier and heavier material or no, not really, but you can begin to get more and more cooler environment. Then, even though it was expanding away and you had these gases, the other forces that we're so familiar with begin to take their whack at producing elements. So as we have a cloud, and imagine it for simplicity as hydrogen expanding out very, very rapidly from a single point. That cloud, if it's in hydrogen, wouldn't be uniform. Maybe there's a little more hydrogen atoms here than there are here. And when you, as soon as you make that an unbalanced part, you begin to have a gravitational storm. The heavier begins to pull in the lighter. And when you do that, you can eventually build stars. And those stars start out as being collections of uncountably large amounts of hydrogen atoms, and they begin to compress together. And as they compress together, they begin to form a new competing environment in which we press that hydrogen together because of gravity, and we want to pull it apart because as we do that, we produce heat. But eventually, we produce the first stars. And eventually, these stars grow or collapse and have their own life cycle. But those stars interact with other stars, and you make solar systems. And finally, when you make solar systems with other stars, you begin to make things around those new stars, which look like our planets. So when we make a star, what we're really doing is producing what I call some of the most violent uh, factories possible for producing elements. Elements in general are really pretty difficult to make. Platinum, gold, and silver are really difficult to make. But we're pretty lucky the universe is very impressive. So we look at a star like a little bit different than our sun, but maybe what our sun will eventually will be. Look, it starts out primarily as hydrogen, but as we begin to pull all that hydrogen together, individual hydrogen or groups of hydrogen atoms may be squeezed together through a process of nuclear synthesis, and we produce heavier element. This is going to be a very complicated process because we have competing things. First of all, whenever you think about an atom, we think about the nucleus, we think about having a positive charged proton. And if we take a positive charged proton and we think of it like a magnet, even though it's not quite the same way, and we have another positive charged proton, if we want to bring them together, they're going to naturally repel each other. On the other hand, if I have an electron and I want to bring it to a proton, they're going to be naturally attracted to each other. So if I want to squeeze two hydrogen atoms together to make a helium, or a group of hydrogen atoms to make a helium, I have to overcome this ability to push apart and be able to combine. When I do that, then certain things in the neutron in particular take place. So our quarks there that'll give us a new force, a strong force that allows us to make this atom as strong, but we also release energy. And that energy is the fusion energy that we all hope for someday for Earth to allow us to move away from fossil fuels and be able to have an infinite supply of energy. As I said, we call this nuclear synthesis. So an example, a couple helium, helium, and helium can make carbon 12. And when we squeeze all those things together, we make energy. But what we have is competing things, as I said before, in terms of being able to squeeze this together to overcome this proton-proton type of uh, repulsion to make bigger atoms. And we call this the binding curve of energy. You can see there on the right-hand graph, we can look at the mass per nuclear particle. So, and then the bottom part is basically the periodic table again, but lined up from on the left-hand side of that, the lightest, the hydrogen, to the heaviest when we count the number of protons and neutrons in a material. And so we come down and we release fusion energy. Then we also are competing as we try to push too much of this together. Then we just have a repulsion energy which overcomes. So in a star, like we just showed there, as time progresses, we're going to make hydrogen to helium to carbon to oxygen. But eventually we get to iron. And by the time we get to iron, we find out that we have to put more energy into the system than we can release when we make the new element. So for stars in general, We can't produce any elements through nuclear synthesis which are heavier than iron. So that means silver, platinum, and gold shouldn't be in our universe unless some other really cool stuff is going on. So it turns out that really cool stuff is going on. And what I like to say is that death comes from life for platinum and gold. When a star eventually has squeezed together all of its hydrogen to make helium and all of its helium to make carbon, and releasing that energy, the heat eventually goes away because it's no longer producing energy, and that material, through a gravitational attraction, squeezes the material and squeezes the material until we're having the actual nucleus interact with the electron cloud of each of the atoms. And this produces a neutral particle, or mainly neutrons. And we end up with basically stars which die, go through a dramatic exhumation, collapse into themselves, and make a big mass of neutrons. So we make neutron stars. And for most neutron stars, the way we understand them is that they basically have a crust, which is complicated materials, but inside is mostly neutrons. A few other particles, but mostly neutrons. So a neutron star is a collapsed core of a large star. And for most neutron stars, which we can observe, they have a mass today of somewhere between 10 and 30 times what our sun is. So they were pretty big stars to begin with. Neutron stars, though, are some of the smallest and probably the most dense objects, not counting something like what we call strange stars or some theoretical things that we can imagine that may be around black holes. But they're the most massive that we can see. But they're really small. A typical neutron star, so that has something like the mass of 30 times of our sun, only has a radius of like 10 kilometers. It's like downtown Manhattan. So if I was able to take, a single tablespoon and travel down to a neutron star, and I take a tablespoon up, it would weigh 10 million tons. So these massive objects that are around contain some really interesting material. They don't really have elements in them, but they do have neutrons, which are an important uh, source of other kinds of things when we want to make something. So if we bring a neutron star and we are able to take a neutron star and basically come to another neutron star, we can have a process which is very different than anything else we've seen in the universe. So we talked about nuclear synthesis. We took two materials, we squeezed them together, and we made a new material. So the nucleus went from perhaps having two protons to four protons. We could have also added one of those protons by just taking a proton and throwing it at enough energy to overcome the repulsion to add on. And we call that process a slow neutron process. But it turns out that if we take neutrons and we do that, the neutron typically enters the nucleus and it decays rather rapidly, producing either a proton or another and a neutrino or some other material. Our process for making gold, or the process for making gold, takes advantage of the fact that if we had so many neutrons in a short period of time bombarding a nucleus, that many of them would have to stick, decay to protons, and we can make a very, very heavy element. And so the R process has to be surrounded by an extraordinary amount of neutrons of high energy. The only kind of place we can imagine that would be was within a neutron star. Well, how do we get those all together? So the way we think that happens is through neutron star collisions. So neutron stars are very massive objects sitting out there, so they're exerting their own gravitational pull on the surrounding area. And occasionally they find a neighbor, which is also a neutron star. And those neutron stars then can begin to have a slow path to collide together. They're pulling on each other so they can what we have called the spiral of death. And when they do that and they collide, in a short period of time, we make a tremendous amount of energy available to make new elements, which are immediately are ejected across the vastness of space. This massive ejection is these heavy elements. And so we can imagine that on this very special case, we could make gold and platinum perhaps and eject it across the vastness of space only to be collected later on. But remember, the vastness of space has material in it at all times, but very, very sparse. So typical uh, segment of when we look at a telescope like the James Webb and we look at a section of space, we call space anything that's less than 10 to the minus 20th our atmospheric pressure at Earth, but it still has material in it. And maybe some of it is gold, some of it's platinum, but it's spread out over tremendous space. So one of the interesting sidebars then is that Einstein predicted that gravity would behave this way, that gravity was actually a shape of space. And so that you should have waves telling you what the shape of space would be if you have massive objects interact. So one of the things that we always have trouble with is gravity is we think about it as, a force that we can go measure. We can turn it on like an electric device or turn it off. That's not what gravity is. It's the actual shape of space. But we can change that shape of space when we have interaction with very massive projects. And so Einstein predicted that if you had the right circumstances, where you have a massive object collide with another massive object, you would take a ripple in that carpet of which we call space, and that ripple would translate out across. As a sidebar, I happen to be at Caltech as a seismologist. This was discussed before in the late 70s when a physicist came running around the seismo lab where we worked and asked, why can't we make seismometers on the North Pole and the South Pole that we can compare the shape of the Earth with time that would help us be able to see these ripples in space? And his name was Kip Thorne. And of course, so each graduate student was asked how they could do this. And of course, anybody that was smart enough kept quiet because they knew Kip Thorne was a really smart guy, right? But they were like, he doesn't know anything about the timing that we have to deal with. We're really happy when we're millionth of a second, but you're asking for shape changes, which are much smaller, that we're going to be dealing with timing that has to be good to a millionth of a second. And so, of course, he left seismologists in frustration for better technologies, and he eventually was able to capture a neutron star collision on camera. And in August of 2017, in one section of space, um, it was observed that two neutron stars collided. To be truthful, I'll take a step back. They built a device to look for these ripples in space, which in the US is called LIGO, which is an interferometer. And it measures the distance between a place in Louisiana and a place in the state of Washington to incredible precision. So it measures that distance and looks at a change in time, or what we would call strain. And on this device, they saw a ripple, which suggested that something strange had happened to space. And they had enough time to be able to say, well, if we've been operating these other optical observatories, maybe we can see where it was in space. And they were able to see this collision between two stars, two neutron stars. What's more amazing is once I knew that was, they were able to take pictures and look at the spectra of material that was being ejected from those neutron stars. And it was consistent to the spewing of gold in particular, and platinum probably, although the spectra was hidden by the other. And we could see in a very short period of time, days, that on the order of 500 Earth masses, total mass of Earth, ejected out that was made purely of gold, along with this other material. And this ejecta then, of course, is spewing out this new material. So we have to have a really, really dramatic event, which is probably fairly rare in the universe, maybe 10, 20 times a year, but the universe is vast, in which a neutron star collides with a neutron star to produce these heavy elements that later on we value as elements or metals for jewelry. From the stars to the interstellar medium, and Sir Francis Bacon, sort of the modern father of the scientific method, looked to the sky and could see these things through the first um, or third generation telescopes and be able to see uh, things that looked like nebula or something was different, and called this the interstellar sky, and was able to say that this interstellar sky was something that we had to be made of. And indeed, these are these clouds that come together to be able to make planets and stars later on. So they must have all the elements after these collisions that allow us to make new materials. Well, somewhere around 6 billion years ago, there must have been a neutron star in our neighborhood of the solar system. And in this neutron star collision spewed out material. This material was collected up, not all of it, but much of it collected up in a gravitational storm that began to form our own solar system. And so our own solar system, as it began to pull this material together through a gravitational interaction, made first a large cloud, and then through a process began to rotate, began to produce a star. And around the star, there was uh, a equatorial plane that contained more material, and those more materials, through centripetal force versus the force of the gravitational, began to form planets, and eventually gave us our solar system with the sun in the middle and 8 planets, unless you still want to have Pluto in there, orbit our planet, and they're part of a process of what we call fractionation. So in the center is a massive star, but the materials that were around that never made it quite back to the sun had a fractionation with heavier materials and close to the sun and lighter materials far out. So you end up with planets that are basically gas giants at the edge of our solar system, and then the rocky planets that are inside the Earth, Mars, and Venus in particular, which had more collection of elements. But this collection of elements that came into our planets was not a simple process either. Yep. Sorry about that. We also collected, as this material came in, um, this rocky material collided through this smaller gravitational attraction, and began to form our planet. This collision of material and making of that planetoid is also a violent process. You're not on a colliding material, therefore producing heat. But as you produce that heat and grow this, you also increase the gravitational attraction of the material around it. When you begin to melt a planet like this, then the elements all have their own pathways through the Earth, and you begin to fractionate and build something like the core, in which was largely iron. And on the outside is materials which are going to have a different melting point and a different attraction. You're going to have silicates. And so as we do this, we begin to separate those collection of materials into a collection of minerals. And those minerals are a reflection of, again, the size of the planet and the ability to fractionate. When it begins to fractionate like that, and we begin to build an iron core, which is much more abundant than some of the heavier elements like this, they'll also find that some elements very much follow where iron goes. And so as we begin to melt and produce a core, we pull much of the platinum and much of the gold out of the Earth's outer area and bring it to the core. The total amount of gold and platinum that's in the core is about 100 billion times more than is in the Earth's crust. If you really want to mine for big precious elements, it's far better to come up with an idea to be able to mine into the Earth's core than send around rocket ships looking for random meteorites that may have a bunch of material in it and bring them back to Earth. But as it did this, we began to build the core, we begin to fractionate, we begin to collect the gold in certain places and collect the platinum in other, in the same, and maybe the silver more or less on the outside. This is a process that's going on, and we reduce planets. But Earth seems to be at a really sweet spot. And so sometime during this fractionation, we began plate tectonics. We're the only planet in the solar system in which we actually revitalize and remake our Earth's crust over and over by having material move around. This is its own factory in terms of relocalizing materials, moving them up sometimes from deep in the earth to spewing out in volcanoes to collecting. And it's this engine that allows us to find these precious jewelry metals in concentrations that allow us to put together. I can't emphasize enough how rare this is, though. When you think about first, you have to have a neutron star collision. Then you have to be able to build a star out of materials that are close enough to collect all those materials out of the interstellar material, to build a planets and have a planet that's able to fractionate that material, but then rework that material through time through plate tectonics. I don't want to say Earth is unique because we got something like 10 to the 22nd planets probably, okay, in the universe. But it's very, very unique in the way when we put all these things together. We're in a very, very special place. My little ad lib here is that when people say that people belong on Mars, they forget how unique Earth is. And the same reason that gave us plate tectonics and give us metals is the reason we evolved there. And so actually our own planet is unique just as we are. Thank God for plate tectonics, because as we rework the Earth's surface, we melt material. We remelt that material often with wonderful fluxes of things like water and so on. And this allows us to build ore deposits. And these ore deposits could be of gold or silver or occasionally platinum. And I'll talk a little bit more about platinum separate from this, and allows us to be in a situation where we can eventually mine that material. And that material then can be used, as we said, in society, but in particular, uh, they're rare but important in terms of what we do for the jewelry metals. So this is typically what happens when we have plate tectonics. We create a melt. That melt builds large volcanoes like the Cascadias today in Oregon and Washington. But eventually, that part of the plate tectonics will cease and will eventually erode those down and will leave behind the remnants of those melts. In the remnants of those melts are things like veins and cores. And so the most famous gold deposit in the world, of course, is the remnants of a much larger Cascadia that was originally eroded, that is the Sierra Nevada. And in there we have things like gold in quartz veins. This happens to be a gold in a quartz vein from Scotland. And it's my favorite gold because it's in my collection. It's from the ancestral home of the Wallaces. This is near a place called Lead Hills. And what you're looking at there is a collision that occurred 400 million years ago between what would become North America and what was become the Eurasian continent. And this is after the erosion long ago of that, leaving this behind. Now, when we think about making minerals, gold or silver or platinum, we have to think about what happens during that process. So if we just look at it as the metal, like I just show you native metal, then you could think about the metal collecting, and the metal collecting can be combined to make a crystal of that metal, so a crystal of gold. And it's simple, pretty simple, at least to think about that as gold. And gold is, in fact, doesn't make a whole lot of different minerals. It's a native element, largely just native element, although there's about 25 gold minerals that are not they're not very common. Gold prefers to form in this native form. And so when we get that, we sometimes get crystals, and our crystals depend upon how we take that gold when it's in the melt and we able to cool it and or at least change the conditions around the pH or the EH to grow crystals. And so we actually can know how that works fairly well. And if we do this crystal growth, we can actually tell you on the basis of how a crystal looks, whether it was a growth rate which was slow or a growth rate which was very fast. Most gold is found by having growth rates which are incredibly fast. They're basically in solution um, a, a molten solution, if you will, or a high temperature solution, usually the gold is carried by something that has either CO2 or chlorine in it. But when they interact with something that changes their pH, so a hot solution with quartz and gold in it interacts with the surrounding limestone or shale, the gold immediately drops out and makes large sheets or crystals. For example, the crystal you see there on the lower left-hand side is from Colorado quartz mine. These sheets of gold, they're very, very fast growth. That particular thing, which is about 11 inches tall, probably that crystal grew within minutes. And it was just simply dropped out of solution because of a change in pH or EH. On the upper figure, which shows actually little octahedrons of gold, those crystals probably took much longer to grow than that large sheet. Now, platinum, on the other hand, is a very, very rare mineral in the wild. Even though you saw that platinum and gold are in the crust about the same in terms of the total amount that's there, native platinum is extremely rare. In the center of this figure is a nugget, a platinum nugget. It's got some iron in it also, so it's not fair to call it pure platinum, but nearly pure platinum. Comes from a locality which I'll talk about shortly in a minute in Siberia. There are about 5 or 6 platinum minerals. They're not very common. There's the two that I show here on either side of that platinum nugget are both sperrylite, and that's a platinum arsenide. And that's other than that, you usually find platinum as a impurity in other elements. But these particular things are incredibly interesting in terms of how that material behaves. So when we look at this, you can see that we have this platinum is coming out, uh, and when it comes out, it's rarely distributed across, and it's usually concentrated in one of 3 ways. The first way that is concentrated is very rare but extraordinarily interesting. That platinum nugget that I just showed there was from a place in eastern Siberia, and it's from a thing that looks like a crater. This is a European Space Agency photograph of a place called Condor, Condar, and it looks like you're looking down the crater of a volcanic edifice. In fact, that's a uh, 6 kilometer across diapir, something that came up from at mantle depths of at least 200 kilometers below the surface very rapidly and built a dome, not unlike what you see when you have diamonds come up through kimberlite pipes. In this case, then it was eroded with time, and you can see the streams coming out of the upper part of that diagram there. Prospectors came along, not expecting to find anything necessarily there, but thinking it was a meteorite crater, thinking they would find meteorites. And what they found is native platinum nuggets and some of these crystals of what are known as isoferroplatinum, another mineral, which is the cubic part, the thing that's on the upper part here. These are some of the, like I said, incredibly interesting geologic process in which you're looking at an earth belch. And the earth belch happened to be very fortuitous. It took this platinum from deep within the earth and allowed it to be at the surface. Another way to, excuse me? Oh, another way to get this material to the surface is to have a large meteorite impact, which also can bring material from deep within the Earth's surface. The most famous of the localities for a meteorite impact generating activity within the mantle that came up and was able to build a mineral deposit is Sudbury in Ontario, Canada. And this map that you see on this right-hand side of the figure is the meteorite came in at an oblique angle, struck, and produced a large depression. And this depression material came up from the mantle around, which was hot, molten, and deposited heavy metals. Nickel and is what it was famous for, but also platinum. What's shown here is a cross section of a piece of ore that I collected there, and you can see the shiny material in there. That's sperrylite, this platinum arsenic mineral brought to the surface, and that's like I said, the second of this ways that you can produce this uh, material uh, for uh, for producing platinum. The third way is one that is poorly understood, but is really important for what we think about how the Earth forms, and also a mark for how we think about extinctions in a time of climate change. Occasionally, we get horrendously large volcanic eruptions of basalt. And the two most famous of these basaltic type eruptions are what are known as the Dedekind traps in India and the Siberian traps in northern Siberia, in the middle of northern Siberia. For the northern Siberian one, basalt came out over tremendous flows. If we took all the basalt that was erupted probably over a 3,000 year period in Siberia and you stacked it in the United States, it would be 100 feet thick. Um, and so this basalt then was bringing up material deep within the mantle, and it was also rich in platinum. And almost all the sparolites that you see in the world are the best ones, come from these kinds of traps. So you have these three things which are allow us to excavate basically deep materials from the earth to give us to our platinum. Now, silver I'd like to call is the most magical of all elements. I happen to be a silver collector, and the reason I got interested in silver was because as a child, uh, the first one of the first really interesting specimens I collected when I was with my father was a silver, which was a collection of coils, curls. I call them the silver curls. And I asked my father why would the silver curl up like that? What caused that? And my father, who was actually a very accomplished uranium chemist, told me, that sounds like a really good problem. Maybe you should spend your time studying that. I was a youngster at the time, so it took me more than 65 years to actually begin to understand it. But it turns out, of course, that what silver has is what I call the magic of the promiscuous electron. So silver has very, very unique properties compared to everything we've talked about. It is the best conductor of electricity of any metal known. So its electron is able to move freely from one silver atom to another, transmitting electricity. But it also has a very special way to bond with sulfur. And so it can make a large number of elements, which we call sulfides and silver salts, which have some really interesting properties. And it also could combine with halogens, so things like chlorine or iodine. And it makes what we call the halides, which produce a bond, which is easily disrupted by a photon and was the basis for photography. And so these things all together make the silver different than what we talked about gold, which is mainly mined as a native element, or platinum, which is mainly mined from places which have been excavated deep in the earth, to large deposits for silver, which usually have many, many minerals in them. And the minerals are a fantastic group of family of colors of things. It can be found in a native element. These are examples of native silvers that you see. Often it's found in very elaborate forms in which you find twinned crystals. The upper left-hand corner is what people refer to as herringbone silver. This particular specimen is about 7.5 inches across, and each one of those rib lines is a lineup of crystals which are twinned. And this one is from a deposit in Charnecillo in Chile, which produced some spectacular other silver minerals later on, but in a short period of time became a dominant silver producer for 4 or 5 years and put Chile on the map in terms of uh, a rich economy. It often forms in wires. The wire there you can see is from very furthest west Siberia is Dukat, Siberia. There's actually gold on the surface of that wire, so it gives it that kind of funny color. And that inevitably grows from sulfides. And it turns out that Michael Faraday, and everybody's heard of the word Faraday's law, long before there was even a notion of what atoms were like, discovered what they called ionic conduction in solids. And he discovered it in a silver sulfide, which became a mineral which we call acanthite now. And he showed that as temperature rise, it was possible to make electricity conduction in this mineral go up. That's the opposite of the typical way. And if it got high enough, silver began to grow as wires itself. Um, Silver crystals are usually sort of cubic or octahedron. One on the left-hand side there is a large crystal of crystals from a fantastic deposit in the upper peninsula of Michigan, the Keweenaw. This particular specimen is almost hand-sized, and you can see large crystals there. And then the last one I show is the cubic crystals for silver from what's known as Kongsberg, which is also sort of the granddaddy, if you're a mineral collector, localities for silver because such great silvers came there for a few hundred years. So I want to just talk a little bit more again about this magic electron associated with silver. If you just add it to a little sulfur, ores abound. So there's a canthite, which I told you Michael Faraday first discovered as the first semiconductor, and his rationale showing you could raise the temperature and then make conduction work go up, therefore exchange the electrons better. This is the main ore for silver, often in fine powders, by the way, throughout the world, but sometimes forms fantastic sets of crystals. The upper one is from Freiburg, Germany. Uh, Both of the upper ones. One of them is again a twinned crystal. If I had more time, I would tell you all about the wonderful twinning associated with the canthite. Um, the bottom two are the first one is the shiny cubes down there is from Guanajuato, which we call the granddaddy of all silver deposits because it's still being mined and it's been mined for over 500 years continuously. And the last one you see down there is fine but small silver sample from the state they live in now in Colorado, from Leadville, which is it has its own history as one of the great silver deposits of America. But the stars of the silver minerals are when you add that same sulfide, but you put in a semi-metal, in particular antimony or arsenic, and you can make incredibly colorful things. These are on the left-hand side, proustite, on the right-hand side, perargite. We call them the ruby silvers because of their colors, obviously. Um, these are really interesting because that sulfur silver interaction is very sensitive to light also. And if you break the bond, by adding a little thermal energy into these. They darken with time. As you break that bond, you produce usually an arsenic or an antimony oxide, and you leave behind native silver. The native silver is on the surface of this material, but you can always recover the silver as you mine that. So I want to put those all back together then. When we got this thing about, we could talk about the mining, we talk about the minerals, we can talk about Earth, we can talk about our solar system, we can talk about um, neutron stars. Really, the story of these metals is one that can't be told by any one part of that. You have to put it or you have to think about it in the context of a geologic arc that begins at the very, very beginning of the universe to building a universe that allows extraordinary, rare interactions to happen, but make time long enough that that other possibility comes together to finally make new minerals that finally make a planet in rare circumstances that finally has enough geologic process to concentrate that we can recover them into those metals that we can make beautiful things. The picture that's on the left there is from the Webb telescope. It's a couple months old. It's actually showing a neutron star. And so the interaction of the light around it is distorting what that image is, but it's a neutron star. And finally, it's going to produce at some point, if there's another one, the platinum we have for the wonderful whiteness and lightness of modern jewelry. So, what I attempted to do today was to give you just a little bit of insight and think about that jewelry is and the metal isn't an accessory. It isn't just the aesthetics, it's our universal history. So I'd be happy to have discussion or questions if you have any there. I'm not quite sure how Ray will moderate that, but uh, I'm happy to have that discussion.
Well, thank you very much for such a thorough covering from the Big Bang to the moment that we're talking right now, looking at the origins and the evolution of minerals and metals, which is, I think, very interesting. What I'd like to say, though, is that when you take a look at the use of these metals, and you see programs like the Antiques Roadshow, you start to see a pattern, and that up until about 1900, when you had a white accent metal in a piece of jewelry to put a diamond in, usually with silver, and then about 1901 ish, they sort of discovered their ability to work platinum, and so all of a sudden, all the white metals in the early 1900s were almost universally platinum because it was so easy. Once you got figured out how to work it, it was actually a very useful material. So I and it's kind of I think people need to know what you've shared with us today. Now, I'd like to ask Clemens if he could look in the chat and see if we have any questions to begin with that are already pre-written.
Yeah, just checking. Lots of congratulations on the talk. The following comment: the meteorite that struck Sudbury would not have hit the Earth at an oblique angle. Instead, what was originally a round crater was deformed post-impact by crucial scale deformation, including pressure from the southeast through deformation in the continental scale, Granville Geologic Province.
So this is a topic. This is a topic often for geologists, and it's correct that if it was a too oblique of an angle, it would be an unlikely thing. And if we do the three body problem, but there's a lot of discussion that how what did that impact really look like, and what did the deformation look like? I would say that uh, there's not a consensus exactly what it would look like, and I shouldn't give the impression that it was truly oblique as that scale is, but I would say that there are a number of models that have looked at what the deformation had been, but also then the chemical mixing, that it probably still could not have been a direct impact, what it looked like. But that's a sort of a relevant point to that. It's a tremendous excavation event, which allowed us to have exposure to this great reservoir of this material. And as Ray described for platinum, I mean, platinum was not really named or discovered until, I mean, it was certainly discovered in the New World in Columbian deposits, and but it wasn't discovered as a separate element until maybe 1750, 1750 to 1760. And nobody could do anything with it really because it was so hard to work with because its melting point is high, it's not got the same ductility, and so technology had to catch up with it, as Ray just said, at the beginning of the 20th century, and suddenly it was a fantastic material. But it was largely uninteresting to people until they figured out this new technology.
Okay, there's another question from David Mustard. The origin of the silver curls.
Well, so, one of the things I don't have pictures of this I should have showed today, silver, when heated, when it's in a sulfide, all sulfides, by the way, does some interesting things. So I didn't really have time to go to talk in detail about this, but silver sulfides and silver sulfur salts all have temperature dependent structures.
Or, oh,
And so as you change the temperature, you go from a structure which is body centered to monoclinic, something else, at a certain point. And so this change in the structure there is, basically something that when you heat that or add energy to the system, that the silver becomes free. It's in a cage, it breaks out from that cage, and when it grows through this phase change, the change in structure, um, it basically exudes the silver. Why that silver curls like that is an experiment that is absolutely fascinating to the new field of nanomaterials. If you can control how that structure and that crystal grows as it does that, then you can make more and more interesting small semiconductors. And so the curl itself is something that people are really, really interested in. And I would say that we understand pretty much what it has to do with is with small defects in the way the silver grows that way.
Oh, oh,
I will also tell you, so 60 years or 55 years of thinking about silver curls, I still got a long ways to go. And so I don't really have the perfect answer for that other than kind of smirk and say, yeah, curls. But it is something that I think that the nanomaterial people will have a much better handle on.
okay, great.
There was a while, I think, where some of the German, Austrian, and Moroccan materials were beautiful wires that had been grown under the flame, where acanthite had been heated up, and apparently I haven't seen it, but they claimed that you could actually watch the silver wire grow out of the material. And I know in sometimes in the Moroccan tents in Tucson, I saw very, very bubbly, almost volcanic looking material in the bottom with nice wires on top. And I would very politely point out to the people that these should be marked as synthesized rather than natural, but whatever.
Yeah, so it's a really kind of a well-known phenomena. I mean, we forget. So when silver mining was really important in the Bohemian region, one of the very first kind of chronicles that were done with this was in 1473. And the description in Old German is watching a person cut a slice of acanthite and then watching silver wires grow actually out of it and the amusement that he got from this. And so we've known that this could be done for some time. In fact, this is not the topic for the discussion here. We actually know how to, it took a long time to figure this out, but we actually know how to tell you whether it was grown in a natural
Right,
environment or not.
right.
Because silver itself comes in two isotopes, 107 and 109. Almost the same weight, almost exactly the same amount in nature. If you grow a silver wire by heating it, and so the silver comes out here, silver 107 is slightly more volatile than silver 109, slightly heavier. And so the ratio of 107 to 109, if grown at atmospheric pressures, is different than if you grow it at geologic pressures. And so by looking at the ratio of 107 to 109, we can tell you if that is a natural or synthesized specimen or one that is grown at more geologic conditions in which we have higher pressures, which do not allow the volatility difference to be recognized by having a preference for 109 compared to 107.
Do we have any more questions on the chat, Clemens?
Yes, there is one more from JP Utras. Any thoughts on the recent paper discussing earthquake-induced piezoelectricity above and beyond pH to rapidly, instantly precipitate gold crystallization? Cool.
So I think that, I think that's, we've known for a long time that gold precipitates fast in faults, and we've seen it in many different environments. And we believe that it was a sudden change in the stress associated with the fluid being injected. So it'd be like an EH change. More recent discussion is that perhaps you can enhance this or perhaps actually control this with a piezoelectric effect. So that works really well in the laboratory on very small scales. And so it does provide perhaps some insight that maybe that can be a natural phenomena. But piezoelectric itself over larger scales, fault long scales, a San Andreas or a section of the Sierra Madre faults, it's much more difficult to keep those organized such that they could have a significant effect. That doesn't mean it won't be proven to have that, but it's still, I would say, is a theory that's not yet fully accepted.
Could I ask the one question of you? Actually, I don't know if you looked into this or not, Terry, but I know in the jewelry trade we have different colors of gold. In fact, in the United States, there's an area in North Dakota, I think it is, where they have naturally occurring multiple different colors of gold, which I think are definitely associated with other different metals that have been and either naturally or manually inserted into the gold mix to change the color. So could you talk about alloys for a second?
And so alloys are really interesting things because it's a special kind of bond, right? And for something like silver, I could go hours on alloys because they really are fascinating what they do with mercury. But that has a separate topic. So when we get to gold and silver, alloys, so silver, copper can easily alloy with gold. A few other elements, but it's mainly silver and copper. And so that gives you this range from gold to electrum color with the silver, giving you this uh, less yellow, but not fully silver, to something that's definitely more apricot-like with some copper. But you're talking about alloys there that are a few percent. And so an alloy itself is a special kind of bond, and you want to make that bond be in there such as you distribute that other element uniformly through it, so it has a structure. And those do appear to, change the spectra that you have from the reflected light, giving you a change in color. I mean, I have a really interesting figure that shows, percentages and how you can make these alloys to change the color from this. But it does definitely change the color in terms of that. It's easy to destroy those alloys also at temperature. So if you take them towards the melting point, alloy bonds typically break in that sense. Most of the time when we talk about alloys, we think about making a material change. That is, if you add carbon to iron when you're doing the refinery, or vanadium, you can make the steel different than you would have otherwise. But it's also an important color indicator. I didn't exactly answer your question that way, but
Well,
it's
that's okay. Yeah,
silver. Copper
one of the problems in the jewelry trade is that a customer will say, well, can you make something? I've got a lot of gold and I'd like you to, can you melt it down and turn it into something? And I usually recommend against it because of the alloys that get oxidized in the process of melting old gold. And because you don't really know what was put into it to make the alloy. And so oftentimes it creates little bubbles in the gold, which show as pits when you're trying to make a piece of jewelry. So that's why, generally speaking, I don't recommend people to melt old gold because of alloys and what they do when you try melting and reheating them.
Yeah, so
Now,
I'm
do you
saying,
have,
yeah, I would
go
agree
ahead,
with
sorry.
you. I
Yeah.
think that else always, like I was saying, alloys are like they're a special class of things when we think about how to be able to distribute silver atoms at, a few percent through gold, so it has the characteristic that it gives you the color of electrum. And but it's easily destroyed with temperature.
Now, Clemens, can we open up the microphones if anybody has any verbal questions, please, for
Yeah,
Terry,
before
so
I,
we
I
can.
still have one from David Mustard. He's asking about the gold concentration in the core versus the iron in meteorites.
Uh, so that's a great question. And so I think where Dave's going with that question is when I collect an iron meteorite, so if I go to Canyon Diablo and I get a big piece of meteorite, how much gold and how much platinum do I see? I don't see very much. Okay. And so the question is, we know that there's concentrations there on the basis of when we look at the full size of the Earth and so on. And so it depends on where the fractionation occurred relative uh, to the center of the solar system. And it also depends upon probably the size of the planetoid that eventually broke up to make the meteorite. So, I mean, we're, it's impossible not to read the news about some, entrepreneur that wants to drag a large meteorite that they've looked at so they know what the mass of it is versus the size so they can get a good guess on how much precious metal and drag it, put it in Earth orbit and mine it. But the fact of the matter is, this is a really, it's a difficult problem, and it's difficult to find the meteorites that are truly enriched because it depended on where they were formed, how far away, and how big of a planetoid they were associated with.
Okay, anybody who has a question, please open up your mics and just speak out. Maybe I will start with the question that I'm interested in. According to the lecture that I'm giving, the one of the biggest deposits for platinum would be the Maransky Reef in South Africa. How was this formed?
So that's a great, and you're an expert on that one, and I probably should have said that. But of course, what you're looking at, I would say that was mainly formed as similar to what you would think of as the Dedekind or the Siberian traps. I mean, you're looking at a chromite type of large scale flat volcanism, and so I think that I didn't include that one, even though some great sparolites are from there, simply because on the surface exposure, it's not nearly as impressive as you see something like the Dedekind trap or the Siberian traps today. But I would say I don't know the age of that exactly, but I think it's around 2.5 billion years old. And so I think that you're looking at something than what you look same kind of physical process, but may have they had access to a slightly different mantle in terms of composition than we see today.
Any other questions?
Yeah, Terry, it was fabulous. I love hearing your talks. And so, a question about Condor. The platinum cubes from Condor often have a surface coating of gold. And the question is that secondary or primary?
A great question. So the mineral, of course, would be isoferroplatinum
Right,
rather than platinum. And isoferroplatinum has a formula of 1 iron and 3 platinums. And I think that if you look at it, it had to have been deposited on the surface of that crystal after it had already grown.
right.
So I've looked at a couple of those that people were willing to let me to destroy. Turns out there's not that many people that are willing to let me destroy there. But almost always the gold content of the isoferroplatinum is actually quite small, but you can get pretty nice gold on the surface.
Right.
And so the only way I imagine you can do that, it has to be after the crystals are already formed.
And you think it's supergene?
I don't think it's super deep. I think
Uh-huh.
that remember the temperatures of formation of these is quite high. And
Right.
so I think that you have a thermometer and a timer that you have to think about that's different than for most minerals.
So you think it's actually was deep underground where the gold was deposited on those
Yeah,
crystals?
yeah. No, okay, I understand where you're going with that. Yeah, I think that the platinum and the gold are both mantle.
Uh, okay, thank you.
Any other questions?
Could we
Well,
go
usually,
a
oh,
little
go
bit
ahead.
afar and ask a really, this maybe you can just immediately discount this one as appropriate, but one of the things I'm most interested in with gold is gold pseudomorphs after pyrite. And I understand that you said that that is not possible thermodynamically to replace pyrite by gold, but you can replace limonite or goethite by gold. Is there a simple formula that I could look at? Either
So I
that,
think uh, Dave, if you send me it, I'll send you the paper. There's a couple
oh,
of really good papers that have been published in the last year in
oh,
which laboratory people have done this process. And directly pseudomorphing gold or pyrite or gold, pseudomorphic gold into pyrite structure is thermodynamically pretty complex. But they've shown some pretty spectacular results in which they go from, you know, um, pyrite to limonite to gold replacing the limonite. And
oh.
if you just, I know you got my email address. Send me something, and I'll send you a couple of those papers. And they're really quite. I would not have thought of this at all, and so I'm really glad to see somebody a lot smarter working on it.
Can you just
Well, I'm
tell me
really
again? I'm
glad.
not sure I've got your email. So what is it quickly?
Well, okay, it's Wallace dot Terry CJR. So I'm a junior
Right. Oh, great.
at gmail.com.
That you were great. Thanks so much. It was wonderful.
Now everybody has that, Terry. You're going to be
I know.
deluged.
Well, I doubt it, but otherwise I'll quickly change it to something else. I've had to do that
Yeah.
before in my life.
Well, I'm actually glad of the research you've talked of because there was a lot of very high-end dealers were getting very upset because of those really amazing looking pyrite looking gold crystals that everybody figured had been faked. And there's been because these guys have a lot of money invested in these, and to prove whether they were real or faked is a very crucial question for them for their investments and for the customers they sold them to.
Yeah. So I think in the end, you have to say that they're possible. And I mean, I don't see any reason right now, after all the work I've done on that those cubes, striated cubes, are not real. I mean, I believe they're real, but I can't say that everyone's out there is real. So the real problem associated with those is they're what unicorn minerals, right? They're unicorn things. They're just this one location that we really see this from, and they're so fabulous. You know, the skepticism window should be high. But the problem is that they were often marketed by dealers that did have other metals which are obviously faked. And so you also have the fog of dealer reputation around that also. And, you know, the same thing is true with the very large, 1992 to 94 Freiberg silver wires. There's a fog of dealer reputation around that, even though the isotope ratios are quite significantly show you that they were done at atmospheric pressure. And so, part of this is everybody wants a certainty around something, but nature's pretty damn efficient at doing everything we can do.
Well, thank you so much, Terry, for taking your time to prepare this and to share it with us. I think a lot of people got more information than they ever conceived they would be able to learn about the origins of the metals that they use on a daily basis in the jewelry world. But this, I hope, gave people a pause to ponder on just how rare and how precious metals really are. And I wanted to thank you very much for taking the time to inform us. Thank you, Clemens, for the time you take from your family and your work to help Gemquest happen. We really appreciate that. And for all those who've taken the time to sit through our presentation today, thank you as well, because I hope that the takeaway from this is that you have a greater appreciation and respect for the metals that we work with and the rarity of the conditions that led up to their actual deposition, and the fact that we can find them in the world that we live in the quantities that we found them. So I think kudos in the end have to go out to the geologists and the miners who've managed to scrape together these minerals so we can use them to glorify the gems that we love so much. Thank you, Terry. Thank you, everybody. And I have to tell you, at the moment, we do not have a topic yet for April because some of the speakers that we had confirmed have backed away because of obligations and time. So I'm hoping that before the next couple of weeks, we'll have out there a new and exciting topic for you to listen into on the last Sunday in April. So have a great day or evening if that's the case where you are. Thank you for all your contributions, your thoughts, and your attendance. And I look forward to, and by the way, if anybody here has a suggested topic, and also a suggested presenter, I would gladly jump on that for future speakers forums, because after 5 years, we're starting to run the well's starting to run a little bit dry in terms of topics that we can speak about. So any of you great creative minds out there who know people or topics we can share in the future programs, please feel very free and open to give me an email and suggest and give me some contact information. Okay. And on that note, thank you, Terry. Thank you, everybody. And I hope you have a great month between now and our next program.